Velocity time graphs are similar to the position time graphs. The same idea, it's essentially the same idea. Rather than stating the position at certain times, we show the velocity of an object at certain times. So the velocity is the y on the graph, and the time is our x-axis. And there are some things that we would find similar to the position time graph. The slope value on this graph is a useful quantity. So let's look at what the slope calculation would be. M would be equal to delta v over delta t. And if you remember from the last lecture, that is the same as our acceleration. So the slope of a velocity time graph is equal to the acceleration of an object. So that's something you should be copying down here. Now, how could we use that? Well, let's look at a sample problem. If this is the velocity versus time for a skateboard rolling down a ramp, then we can calculate the rise over run. And we can do this. Let's look at for some points that seem to match up nicely. At 10 seconds, it appears that we have 30 meters per second. So let's do 30 meters per second divided by 10 seconds. We would end up with 3 meters per second squared. And it does say that the velocity is directed south, so that would be 30 meters per second squared in the south direction would be our acceleration. There is something else, though, about this graph that's interesting, because not only can we use the idea of the slope being the acceleration, but we can also find the displacement of an object by finding the area underneath the curve, or the area underneath the line. So how would this work? Well, if our y-axis is our velocity and our t is our time, then velocity in meters per second times our time in seconds would leave us with meters, and that meter measurement that we have left would be our displacement. So this is easy to calculate when we have a graph that starts at 0.00 and has a triangular area. In this case here, we have the velocity, it says what's the displacement at 10 seconds for the skateboard. So the area of a triangle is 1/2 base times height. 1/2 times 10 times 30 is equal to 150 meters. And because we were directed south, the displacement is south. Here is a more complicated graph, though. It says, what's the displacement represented by the graph over the time interval 0 to 5 seconds? Well, from 0 to 5 seconds, it is the area of it would be a triangle. So 1/2 base times height. Here we would have a height of 10. A base would be 5 seconds. So 10 times 5 times 1/2 would be 25 meters. And that's directed, or that would be displacement in the south direction. Part B, though, is going to say, what is the displacement from 5 seconds to 10 seconds? Well, from 5 seconds to 10 seconds, it is a rectangle, so the area is length times width. The length of the rectangle is 10 minus 5 seconds, so that's 5 seconds, multiplied by the height, which is 10 meters per second. So our area is 50 meters south. And the next part says, what is the total displacement? Well, here we just have to add those two areas together. So the 25 meters south from part A, which is the triangular portion of the graph, plus the 50 meters per second south from the rectangular portion of the graph, that gives us a total displacement of 75 meters in the south direction. So for a velocity time graph, it is a graph that describes the velocity of an object with respect to the time. The slope of the graph is the acceleration. The area under the graph is the displacement. And let's look at some more complex velocity time graphs. So here we have 3 different types of motion, A, B, C. So velocity This is very similar to the other graph we saw, but now it's a velocity versus time, not position versus time. Let's describe what's happening here. In section A, we start off with 10 meters per second in velocity, and we accelerate for 5 seconds till we get to 30 meters per second. We then keep our velocity steady for time period B at 30 meters per second, and then we decelerate until we stop during time segment C, and the stopping time is 5 seconds. So we go from 30 meters per second to 0 meters per second in 5 seconds. So what's the average acceleration for each time segment? This is exactly like it was in the other graph, so I'm not going to show it again, but it is 4 meters per second squared south for segment A, 0 meters per second in segment B, negative 6 meters per second south, or the way I would prefer you write it would be 6 meters per second north. 6 meters per second squared north, I should say. And our last slide here, this is the interesting part, because now we have to find the displacement. And this isn't as easy as it was because we don't start at 0, 0. That area under A includes both the triangle and the rectangular portion from 0 to 5 seconds up to 10 meters per second. So let me just switch my camera on. Oops, and I can show you how we can calculate this. So we have our area under A. So let's call this displacement. Oops, sorry, displacement A is equal to the area of a triangle plus the area of a rectangle. That is 1/2 base times height plus length times width. 1/2 of the base. The base here is 5 seconds. The height is it goes from 30 to 10, so that is 30 minus 10. I'm going to drop the directions because this is going to get a bit, there's going to be a bit to write here. The length of the rectangle is 5. The height is 10. So altogether, the displacement of A is 1/2 of 20, which is 10, times 5, which is 50, plus another 50. It should be 100 meters. And that is in the south direction. That's our displacement for A. Now let's move the camera over. Look at our displacement for B. And the displacement for B is simply the area of a rectangle. This one's a bit easiest because we don't have any motion. That is the length times width. And the length here would be 15 seconds minus 5 seconds. The height here is, or the width, would be 30. That gets us to 300 meters in the south direction. And the displacement for C is equal to the area of just a triangle, 1/2 base times height. The base is 20 minus 15. The height is 30. So that works out to 1/2 of 30, which is 15 times 5, 75 meters south. And we would finish this off by finding the total displacement, which is the individual displacements of A plus the displacement of B plus the displacement of C. That equals 100 south plus 300 south plus 75 south And all together we get 475 meters south. And that is our final answer for that question.